Yes, and the next speaker is Professor Jennifer Mather from the University of Lethbridge in Canada, and she is working on these wonderful creatures, cephalopods, with an octopus, and these animals have the biggest brains, at least absolutely, of the invertebrates, so the animals without backbones. And not surprisingly, people have thought for a long time that maybe they do have some kind of cognitive abilities. And a lot of research in recent years has suggested that that is in fact the case. So I will not take any more of your time. Jennifer, a very warm welcome, and I'll leave it to you.
And thanks to the organizers for doing this. I might say actually that we speakers are just as fascinated as you are with each other's presentations, and we're learning a lot. And I don't have anything as sophisticated as Lars' beautiful studies. I think what I really want to tell you more now is the context in which cephalopod intelligence has probably evolved and the specialties that it probably has. There are many, many, many spin-offs of studies that we will be doing in the next few decades, but right now we're very much at the beginning. Okay, but I'm also assuming that people don't really know about octopuses. I think that's fair. So obviously, one of the most important things about the octopus is the large eyes. And you see the octopus kind of standing up, looking to see what's going on. It's a cephalopod. That means head foot. And the reason that it's a head foot is that the head is right next to the arms, not feet. Okay, and that what we think of as the central body, all the internal processing, is down behind the head. This particular picture is, it's kind of like you could say it's a praise view, but it's also probably an action view. That's the ventral surface, and you see the sucker-lined arms and the central mouth. Okay, so when you're looking at the dorsal surface, you're looking at not really the action surface. Now, the thing about cephalopods is they are not related to the vertebrates that people generally study cognition in. So, of course, whoa, I knew I was going to do that. Mammals and birds, which are thought to be the models for flexibility and intelligence, they're fairly closely related to one another, but if you look at the relationship for them to octopuses, no. So they really are, and this is the interesting thing about it, they're really a different evolutionary route to the development of high intelligence. And that, of course, is why we study them, because it really is, at that point, comparative cognition. Just a reminder of what intelligence is, and this is Alan Camel, Processes by which of animals. And what's interesting about this is you're obtaining information, processing it, storing it, figuring out how to use it, and then using it. And that's the gist of intelligence, the treatment of information centrally. Okay, now this I take from, sorry, from Clayton and Emery, thank you, Nathan, who said, well, we think the ecological conditions for high intelligence are as follows. Long lifespan, okay? Many, many months and years in which to learn. Think of the elephant, think of the human. A pervasive social group. And of course, those people who are finding very interesting processing in birds are looking at social groups. And Lars is looking at social groups in insects. And of course, humans are social primates by and large, are very social. Long periods of dependence, okay? So for a human, anybody who's raising children knows it's at least 20 years. But you're not just dependent in the sense that you can learn, you're also protected from the difficulties of the external environment. You're not having to make life and death decisions immediately after you're born. Another thing we think is important for the evolution of intelligence is a varied diet. A generalist who has to learn where food is, what food is, how to deal with it when you've got it, very important. And the other thing is a variable, challenging environment. the kind of environment you find in the rainforest where many different species of trees that produce fruit, the monkey has to learn which ones are where, when they produce fruit, and generally to cope with a very difficult food environment. Now, if you take these 5 and you apply them to cephalopods and say, okay, so why would these circumstances result in evolution of high intelligence? Nope, they don't have a long lifespan. The mean lifespan's a bit over a year. And the giant Pacific octopus that get to 25 kilos, their lifespan will be maybe 2 to 4 years. It's unusual, but not a lifespan. No, octopuses are solitary animals. There's no evidence that they have real social grouping. In some circumstances, I think particularly when they're crowded, yes, they have developed hierarchies, but it's not really normal. In fact, they're cannibalistic. So the next one down there might be as interested in eating you as in being your friend. And no, long period of dependence, not at all. Cephalopods produce many small eggs. The size of the giant Pacific octopus eggs are the size of a rice grain. And they hatch to a paralarval stage, float off in the open ocean, and then maybe even months later settle on the bottom and begin to develop this benthic lifestyle that we study. So the answer is it must be that the animal is a generalist in terms of what it finds for food, and that within this variable, challenging environment, think of the coral reef. Think of the number of different species. Think of the number of fish species that are out to get you, okay? So it must be that this is the evolutionary pressure for cephalopod intelligence. Now this, I want to take a little bit of time with this, because the cephalopod isn't built like us. We have a central brain. When we look at the number of neurons in the brain, when we look at the size of the brain, we say, yes, of course. This is perhaps an intelligent animal because it has a large brain. In terms of number of neurons, the octopus has more than rats and more than pigeons. But 2/5 of the neurons are actually in the brain. 3/5 of the neurons are out making this very complicated muscular hydrostat arm movement system work. So what we have to realize is that the animal isn't making a central decision, programming it, sending it out to the muscles to do, monitoring it, and controlling everything. Okay? There's a huge subset of neurons in the arms. And it's difficult. We're not exactly sure to what extent vision, and they have very good eyes, controls their behavior. And we're not sure the extent to which these subroutines, which is the only way I could call it, in the arms, are actually doing a lot of the processing without central monitoring, okay? But the octopus actually has three regions you should pay attention to. The brain, which does the cognitive processing. And let's see, you can see that there, that the brain is controlling motor commands going to the arms. It's controlling information going to the skin system. It's processing information coming from the eye. But look at what the subroutines are that are there in the arms. There's a dorsal nerve cord that runs down every arm. It's actually a bunch of ganglia. There's a ganglion above each sucker, and then there's another sucker ganglion below. The brachial ganglion controls and interacts with the sucker ganglion, each its own sort of subsidiary ganglion, and the brachial ganglia control back and forth to each other. And it's got 8 arms. There's a commissure around the 8 arms. Sad to say, it was something like 1910 that the only study done on what this commissure is doing was produced. We know it's important, we just don't know what it's doing. Now the other thing that's important about the cephalopods is, as I said, I knew I was going to do that. The display system in the skin is fabulous. Octopuses are the real chameleons, okay? They really put chameleons to shame. And this one is controlled in the brain, but we're not sure to what extent the brain is actually monitoring the result of these appearance patterns. Okay. I tell you a little bit about it. There's a layer of chromatophores in the skin surface, and these are elastic sacs with muscles pulling them out. And then they've got direct neural control for the brain. What that means is that they can be expanded or contracted in 30 milliseconds. It's immediate change, okay? They're red or yellow or brown. But when they're contracted, there are reflective surfaces below, leucophores and iridophores, that reflect back ambient light. So of course, if you shine a bright light on it, it looks like white. But if you're down about 10 or 20 meters, it looks blue because the rest of the light has been filtered out. And here's an octopus not looking like an octopus. Okay. What's important about this appearance system, though, is not just the chromatophores. So the chromatophores expand and contract, and what's underneath reflects when they're contracted. But you've also got texture on the skin. There are muscles in the skin that raise the skin and papillae. And this particular lovely little animal, those are the papillae over the eyes, and they are so conspicuous that we call them horns. But they're not permanent structures. They can be collapsed. Now, actually, the eye is there. Notice there's a white splotch below the eye that acts as a distractor, because eyes are an important signal to predators that there's an animal there. So any animal that is disguising itself probably wants to disguise the eyes. Okay, there's an octopus in each of those pictures. I have fun doing this. This one, below this line is the octopus, and above it is the background. Okay, you can actually pick it up by the funnel, which is the exhalant siphon from the mantle, which is respiration and also it's jet propulsion. But if you look really, really closely, there's the pupil of an eye, and there's the pupil of the other eye. Okay, I told you they were good. Now, this one, there's the body of the animal, and those are the eyes. And a couple of these things, which are like, they look like algae fronds, are arms, okay? So you can see this is a very, very effective system. Okay, I have to try and do this. Now, when we think about locomotion, and you think about 8 arms, it gets pretty complicated. So you have these 8 arms. When the octopus is walking, the back arms will be used for pushing, and the front 4 arms will be used for exploration, okay? But they have lateral eyes. So what that means, I mean, when you think of us, we've got binocular eyes and we go straight ahead like this, okay? But they have lateral eyes, so they're guided in their walking, generally speaking, monocularly. And they do tend to come straight forward, but they don't have to. They can walk like this, and they can walk like this, and they can walk like this. And in each case, what they're doing is allocating the front arms for exploration and the back arms for propelling them. Because they're monocularly guided, they don't actually go straight ahead. They can go in any direction, but the mean heading is 45 degrees or 45 degrees. Okay. Now, when we walk straight ahead. We're guided by these binocular eyes, and we walk straight ahead. When the octopus walks, it decides which direction it wants to go, and since it's radially symmetrical arms, it can go like this, or it can go like this. I can't do it. Okay? We have to, if we want to go that direction, we have to turn and go that direction. but the octopus just goes that direction, okay? So it's much more mobile than we are. And it's very, very interesting also that they have no gait pattern. So when we think of us walking left, right, but think about horses with trotting and galloping and pacing. There are fixed sequences. There aren't any in octopuses. Actually, I should, I don't know how. Well, this is a video, but I'm not quite sure how to start it. But that's okay. I'm going to run out of time anyway. Now, the brain is the computational center of the octopus, okay? And it's got two areas, one of which is a storage area for visual information, which is the vertical lobe, and one of which is the storage area for tactile and chemical information, which is the subfrontal. And the vertical lobe there are two large, very conspicuous optical lobes right behind the eyes, and then the vertical lobe is storing information. So it is the command center for the octopus. It's just not the only area where any processing is carried on. And so I thought I'd show you some of the different things that octopuses have been proven to do in terms of learning. Okay. It has to be based on ecology. And I worked out this diagram from many different sources of information a couple of years ago. It's in the book on cephalopod cognition. I think one of the basic things that cephalopods need to do in order to survive is to get food. But the computation of how to get the food and what to do with it is complicated. So I think that all of these different pieces of information. The octopuses have very good spatial memory. They know where they are. And when they go out to forage, they know where their home is. Unlike something like a bee, though they do not stay in the same place for very long. The octopuses that I watched in Bermuda, on average, were staying in the same home for 10 days. The other thing that's interesting about what I found is that when they foraged in this direction one day, and then they came back to the home the next day, they would go to a different area. So they're probably very often wind switch foragers, which is quite the opposite for most animals. It means when I find a crab underneath that rock, when I come back, I don't go the next day because another crab is not magically going to appear under that rock. Okay, this is just not the way it works in nature. So they learn wind switch rather than wind stay foraging. And when you think about going out to find food, they have to calculate what they've done previously, where there's a likely place to find food, whether they're hungry, whether there's a fish hanging around hoping to get them. So there's many complex features that go into making the decision to leave. Now what's interesting about this is they will do primary search visually. They will go to likely places. And then, like this octopus that you see there, they'll use chemotactile search to try to find hidden food. In the marine environment, nothing is sitting out waiting to be eaten. If there's something on the surface, it's either poisonous, repellent, or has such a good clutch on the rock that you can't get it off. Okay, so they have to use this two-stage foraging. And I think this means that the motivational bases for octopus behavior is a complex of fear, everybody's out to get me, and curiosity and exploration. They're really tremendous explorers. They've got all these arms to explore with. They not only explore, and Kirsten was saying that they're like orangutans. They take things apart, okay? And eventually, if they're bored, they play. So this is the basis for not being food. They have to, and I was reading a review paper that was talking about fear and anti-predator behavior from many different animals, and they looked at the distance at which the animal tried to escape. Well, but that's not what the octopus is doing. The first thing it's doing is it's hiding. And many, many octopuses are, in fact, time-minimizing foragers. So they are hiding most of the time and only getting out to get food quickly and bringing it back. Okay, so the first step in not being eaten is simply to be in hiding. When they come out, and you've seen this, the second step to not being eaten is simply not to be visible. But if they are seen, if a predator approaches fairly quickly, they have startled behavior. They change their visual appearance. And if the predator still approaches more quickly, then what they will do, yes, indeed, they will leave, and they will generate an ink cloud so that the predator can't see them. And this seems also to interfere with the chemical sensing of fish. So not being found is absolutely critical. This particular octopus, which has a crab, will be hiding in this shell. Yeah. Now, Clayton and Emery, Emery and Clayton also said that they thought that there were cognitive operations that indicate an intelligent animal: causal reasoning, flexibility, imagination, prospection. And I might have to go quickly through these. I'm not quite sure how to activate the video. There's a video, but I don't know. It doesn't work if I touch it. Anyway. Okay. This is a skin display. Okay, and if it goes there, do you want to stay here for a minute? I'll see, because I wasn't sure that I could repeat it. What the octopus does with this skin display is puts a dark dark blotch on the skin, moves it towards, and in most cases it seems to be prey that it has tried to catch and lost sight of. So this is trying to get the prey to move. And you'll notice also, because we are going to get it again, that it's dark and white beside it. So what that gives is a line, okay? And line and edge between dark and light. And this is a very good stimulus for pretty well every visual system. Okay, do you want to, so. Can you do it once more? Notice what I love about this is that nothing actually moves. The craniophores expand and contract. So this is, for people who know about human perception, this is apparent movement. Okay. Someone knows. Flexibility. If the octopus goes out in a soft bottom background and it really can't find a good place to hide, one of the things that they're very good at doing is using human trash. But you see what happens, they will have a home underneath a rock, hiding in between a bivalve or a gastropod shell. Or they'll dig a well and put rocks around, or they'll use human trash. By the way, a beer bottle is an absolutely perfect octopus home. Okay, which leaves me with a real problem, because no, I don't like us littering the marine landscape, but what do you say when you say, oh, clear up all those beer bottles, and then my octopuses don't have enough homes? Now, I have to explain that I have no picture of this, but there's several anecdotes. All the cephalopods will extend an arm or a tentacle, and sometimes the cephalopods will do this when they're buried. They'll wiggle it and pale it so that it looks like a worm. So some unsuspecting animal will come along thinking that, like the anglerfish, exactly like anglerfish, but they just do that. They also play using the water jet or using arms. And they have prospection, which is, Kristen probably will tell me I'm not really accurate at saying this, making a decision about a situation that will happen in the future. Okay, so they're octopuses that want to go out in the soft sand, won't have any place to hide, and they will dig up the two halves of a coconut shell, carry it out, And when they want to stop and hide, they'll bring it up over top of them. And this really is planning for the future. Okay, so there is not enough time, but I've done my best. It's a very different mind. It's organized differently, it's got just different subsystems to control, but they are planners and thinkers. And I want to say how many people have helped me, particularly in the field research. I'm spoiled, by the way, this is Morea in French Polynesia, and that actually is me. There wasn't an octopus, I was looking for one and I couldn't find one. So happy to answer questions. I think I only went over about 2 minutes. And by the way, don't do this, because octopuses can bite. Don't do this unless you have a dive glove on. But I couldn't find a picture for this with the dive glove. Thank you.
An octopus lose an arm, can it be replaced?
It regenerates the arm.
It will regenerate.
It takes time. It may take a few weeks, but yes, it starts from a very small piece.
Okay. And does it require a specific brain? Does it require a specific brain to replace an organ?
Sorry, does it what?
Does it require a specific part of the brain to replace a loose organ?
I don't know. I don't think so. I think it's an automatic physiological repair.
Okay, but like a sea star can replace an arm.
Yes.
Yeah.
Yeah. And I don't know why the physiologists aren't studying this, because humans have many catastrophic accidents, and nobody's quite figured out how to get us to act like a sea star or like an octopus and just simply regrow it.
Yeah, you said octopus might have a different mind from us.
Sorry, may
but
have
I
a different
think
what?
A different mind.
Yes.
You said, but I think from a neurobiological perspective, it may be the same as we have or as a honeybee has. Because if we study at a cellular level the mushroom bodies of a honeybee, or the vertical lobe of octopus, or the neopallium of birds, and our cortex, it basically has as a network the same arrangement, the same working memory network for very quick learning. They're all some output neurons, large output neurons, many small interneurons, and the same in the vertical lobe and in the mushroom bodies and our cortex. So maybe the output may be different, but the basic instruments probably has evolved one time and applied many times. It doesn't, in size, doesn't make so much difference. It's a basic circuit that's been invented and told. And if you have many more, then you just quantitatively have many more, but not
But I
basically.
didn't say it wasn't neuronally similar. I suspect it is, though we don't know. So the neuronal circuits are probably quite similar.
Yeah.
The organization of the brain is quite different.
Of course.
And the kind of ecological problems that the cephalopod faces, and particularly not having social relationships.
Of course.
So the whole circumstances are different. But yes, I think you're probably correct that when we know about the connectiveness of the neurons, that they will be the same basically.
Quick
So
calculation, quick learning. This must be done by a neuronal network, and this is the same, I think.
But it depends what level you ask the question.
Yeah.
And you're answering at a different level that I was asking. Okay?
Yeah, of course.
Yeah. How's our time?
Yes, any other questions? No? In that case, thank you very much, Jennifer.